In this problem, we are given the following circuit diagram. We are also given the phasor voltage, and then we are told that the voltage source delivers power to the circuit, which is the load for the following questions. For part A, we were asked what is the peak value of the instantaneous power delivered by the voltage source. So peak value of our power is basically Pmax. So we want to find the power max. If we look in 10.5 of our notes, power calculations, we are going to find the following formula. It's going to look something like this, where we find our Pmax, and then for part B, it'll actually solve our Pmin. Now, there are two important things to note. The voltage source delivers the power, and the circuit is our load, so our circuit will absorb the power. That means we have power going out of our voltage, and then eventually we're going to have some power coming back into our voltage. Since they're going in the same direction, they're going to be the same sign. We're looking for the amount of power delivered. And this again is our Pmax. So we're going to have to find that. And to find that, we need to find our P average, and we also need to find our Q. To do this, we're going to look in section 10.1 at the very end, instantaneous power, for the notes linked below the like button, and that will give us this equation. We can see that our power is equal to our P average, and our P average is equal to the large formula that is above it. In section 10.2, near the end, we can find our Q like this. This will be the equation for it. And now we can start solving. We know our Vmax, it's given right here, 240, and this is given to us as our Vmax, not VRMS. That's important to note. But what we don't know is our Imax. We don't know the current, and our Imax is going to be equivalent to our IS. And to find this, we're going to use Ohm's law, where we have the Vmax, which is the Vg in this case, over our impedance max, which is the T of H. So we can rewrite this as 240. However, we don't know the impedance, so we need to actually find the impedance. We have two impedances here. They are both in parallel. So we're going to use the parallel formula for impedances to solve this. This is 1 over our first impedance plus 1 over our next impedance, which is given to us as negative J360. This is just the conversion of a capacitor to impedance from this capacitance right here. So we're going to write it as negative J360. And this is all being raised to the negative first power. Now we're going to solve for this. This is going to be our new equation. Now we need to convert this to polar form so that we can solve for it. Now we need to convert this to polar form so we can divide the numerator by the denominator, and then we can plug this impedance back into our equation for Ohm's law to find our current. To do this, I'm going to multiply both the top and bottom by 480 plus J times 360. And this is going to be our equation. The way we did this is we factored this in to the top part, and we did the same thing in the bottom. We factored this and this together. If the J's are combined, like up in the numerator once and the denominator once, they're going to become a -1. That's if we have two J's. And this is again what we're going to get. Now we need to convert these into the rectangular form so that we can divide. To convert to rectangular form, we are going to say that our Zmax is equal to the square root of our real number squared plus our imaginary number squared. And then we're going to have our angle is equal to tangent -1 of our imaginary number divided by our real number. I had an extra 0 here, and I deleted that because that is not correct. But after we do that, this is going to be our equation. Now we need to divide our real numbers, so we're taking these two and dividing it, and then we're going to subtract the denominator angle from our numerator angle. We're going to get 288 with an angle of -53 degrees. Now this is going to be the polar form for our T of H. We have found that, and now we can plug it back into our Ohm's law for our current. We're going to have 288 with an angle of -53, and we need to convert the top to polar. This is just going to be 0 degrees. And once we do that, we're going to just have 240 divided by 288. This is going to give us approximately 0.83, and the 3 is repeating. And then we're going to have an angle of 53 degrees. Again, because we subtract the denominator angle from the numerator angle. That is the polar equation for our Imax. Now we are going to find our Pmax, but before we do that, we're going to find our P average, our P, and our Q. So our P average is equal to P, And this is equal to our Vmax, which is 240, times our Imax, which is 0.83, and this is repeating, divided by 2, times the cosine of the angle for our theta v, which is the angle, 0, minus the angle for our I, which is theta I. This is going to give us negative 53. And this is going to give us approximately 60 for our P average and our P. Now we are going to solve for our Q. Our Q is going to be similar. The only difference is that we have a negative sign out front, and this is being multiplied by a sign. This is going to give us a positive approximate 80. Our Q is set to be negative, so we are putting this as a negative Q. And now we found our Q. This actually answers two parts of our problem. So in part D, it asks what is the reactive power delivered to the load. This is going to be the negative 80. Then we're asked for the average for part C. This is approximately 60. And now we can solve for our Pmax and our Pmin. We're going to get this as our Pmax and our Pmin equation. This is going to give us 160 for our Pmax. And then for our Pmin, we are going to have a negative 40. However, since, again, as we described earlier, they're going in the same direction, and this is being absorbed, we are going to have a plus here. For part A, we'll have the 160, and then for part B, we are going to have a 40. Now, to solve for part E and part F, we're going to have to look in the notes again, section 10.2 at the very end. And this is where we have the equation for our power factor and for our reactive factor. Our theta V, we know to be 0 degrees, and our theta I, we know to be 53 degrees. So we're just going to plug both of these into the equations. So for part E, we're going to get 0.6 for the power factor of the load. And for part F, the reactive factor of the load, we're going to get approximately negative 0.8. And that's how you would go about solving for this problem.